So today we'll be talking about the interesting topic of adversarial examples in machine learning. Uh, it's one of the hottest research topics in not only deep learning but also machine learning in general. Um, so we'll be going over uh, the definition and an introduction to adversarial examples. We'll talk about why deep neural networks are vulnerable to adversarial examples. We're going to show how these examples can be exploited to attack machine learning, not only machine learning classifiers, but also we'll go over attacking deep reinforcement learning as well. And we'll briefly touch upon the current state of mitigation techniques. So as you can see, and as you're probably aware, DNN classifiers, deep neural network classifiers, are currently performing at or above human level perception. So in object recognition back in 2013, 2014, it was Szegedy, I believe, who showed that deep neural networks, especially convolutional neural networks, are performing at a higher accuracy than how a human would classify objects. And the same applied to face recognition as well. So in the image that you see here, both of them are the same person, but it's slightly difficult for us to correlate these two images. But a DNN classifier can easily identify the fact that both of these are the same person. Now, what are adversarial examples? In the domain of image classification, an adversarial example is an input to a classifier which is intentionally perturbed to fool the classifier, to make the classifier, to make a mistake. So in this example here, we have an image of a panda which is classified correctly by a CNN classifier, but when we add something that looks like a noise but is actually strategically created, intentionally created, the image still looks like a panda to us as human beings, but a regular CNN classifier is fooled into classifying it as some sort of bird or some other object in the training set. A little bit on the history of adversarial examples. So it's not a new concept. Even as early as 2014, people were looking at ways of fooling classifiers for purposes of evading spam filters. So those weird emails that you get with weird titles and intentional misspelling and so on from the Nigerian prince and all others are essentially ways of evading filters, spam filters. Now, back in 2013, Big U and Szegedy, almost at the same time but separately, came up with a very interesting discovery that image classifiers, especially neural network-based image classifiers, are both susceptible to adversarial examples, which means the type of images that can fool the classifier into making an error. In 2014, Goodfellow introduced a method for crafting those adversarial examples, or essentially he introduced a method for creating manipulations or perturbations that would make an input image into an adversarial example. And they call their method fast gradient sign method. In 2016, Paperno and Goodfellow published a paper titled Practical Black Box Attacks Against Deep Learning Systems, which exploited something called transferability in adversarial examples. So when an adversarial example is found or crafted for a certain classifier with certain hyperparameters, in more than 50% or even more than 80% in regular image classifiers, the same adversarial example is going to cause the same effect, same misclassification in other models trained on the same dataset or similar datasets. And it's called the transferability of adversarial examples. So in this paper, Papineau actually exploits this transferability property to create practical black box attacks. And in 2017, Professor Monir and I proposed the first actually type of attacks on deep reinforcement learning, more specifically deep Q networks, utilizing adversarial examples to manipulate the policy learned and manipulate the actions taken by a DQN agent. So, first of all, let's make something clear. Adversarial examples are not specific to deep neural networks. Back when Szegedy and Bigio's work came out, there were quite a lot of news articles talking about how adversarial examples are the doom of deep neural networks, and it's just DNN's deep learning that is susceptible or vulnerable to adversarial examples. But adversarial examples are actually quite common in different models, different machine learning models. So what you see here is an example of how adversarial examples are applied to fool a linear digit classifier. What you see here is actually an MNIST classifier. And the row over there, the row in this image, represents the target class. So it's a targeted adversarial example attack. In the first row, the last 9 contains noise, perturbations that aren't perceptible to us as human beings, but those perturbations actually make the linear digit classifier to classify the last 9 as a 0. In the second row, the 9 in the yellow square is classified as a 1, and that's due to perturbations that are intentionally added to the image. In the third row, the 2 9s in yellow squares were classified as 2s, and so on. So you can see that even linear digit classifiers are susceptible to adversarial examples. What about other types of classifiers? Well, as we just discussed, linear models are susceptible, and vulnerable models include logistic regression, softmax regression, and support vector machines. Decision trees are also vulnerable, and even nearest neighbor approaches are vulnerable. A more interesting question here can be, what about human brain? So most machine learning classifiers, especially neural network classifiers, are trying to emulate the learning process of natural brains. And when they are vulnerable to adversarial examples, we may be too. The image that you're looking at here is actually not a GIF, it's not an animation, it's an optical illusion. Optical illusions are the natural parallels or natural occurrence of adversarial examples. It makes you wonder whether you can use the same concept in manipulating thought and actions of human beings too. That's something that we'll get to later in investigating vulnerabilities of deep RL. So why do adversarial examples exist? Is it because we do overfitting? Well, overfitting was actually the prime suspect when Goodfellow and his colleagues started investigating this phenomenon, but it turns out, and it's actually a recent discovery, or at least recently published discovery, that adversarial examples are due to linearity of the deep neural networks. I know that deep neural networks, or neural networks in general, are famous for being able to learn nonlinear models. But as you can see here, a rectifier is piecewise linear. A max out function is piecewise linear. And the same happens in LSTMs and even sigmoids. So this linearity is actually one of the major factors in existence of adversarial examples. We talked about FGSM before. So fast gradient sign method is one of the earliest methods introduced for crafting adversarial examples. It's essentially the same as an optimization problem, and the goal of this optimization is to maximize the error incurred by a certain perturbation while keeping the distance between the perturbed image and the original image below a threshold. This specific condition is put into create images that aren't too different from the actual original image, but at the same time they are able to fool the classifier. And we also talked about black box attacks using transferability. So this is how transferability attacks work. The adversary begins creating and training a model on the same dataset or a similar dataset that the target model is trained on. And it finds or crafts adversarial examples or adversarial perturbations to inputs for the dual model, for the model that the adversary is trained. It turns out, as we said before, the adversarial examples that apply to one model are transferable to other models as well. So the adversarial examples crafted for the adversary's model can be simply applied to the target model, and in most cases, more than 50, or in some cases it's more than 80% of the time, those adversarial examples are transferable or applied to the target model as well. There is an open source tool called Clever Hands, which can be used for experiments and essentially generation and crafting of adversarial examples. Clever Hands is maintained by Goodfellow and Paperno, but it's an open source project, and I believe in the past 6 or 7 months since it was first published, there have been many different contributors to the project. You can find it on GitHub if you Google it. And Clever Hands is actually named after a clever horse. So Hans was a show horse in Germany, which, the owner of Hans claimed that it is capable of doing algebra. So people came to the show, a show put up by Hans's owner, and they gave the horse very simple algebraic problems, like what's 1 plus 2, and Hans stomped his foot 3 times, 1, 2, 3. And so on. It turned out later, during a more scientific study of the phenomena, that Hans was actually looking at its owner's face, and whenever the owner nodded, it meant that Hans should stop stomping. So Hans didn't know how to solve algebraic problems, how to calculate additions and multiplications and so on. He just learned a very simple heuristic on how to make his owner and the audience satisfied. And essentially what this refers to in the domain of machine learning is that DNN, or most other classifiers, don't learn the actual function, but they learn a heuristic to satisfy the user. And that's what's being exploited by adversarial examples. So what about adversarial examples in reinforcement learning? For those of us who are not familiar with reinforcement learning, it's a third class of machine learning. So you're probably familiar with supervised learning and unsupervised learning. Reinforcement learning, on the other hand, is actually an interactive way of learning based on the concept of conditioning. So a reinforcement learner, an RL agent, performs an action in the environment, and that action changes the environment. The change in that environment is going to generate some sort of reward for that agent. And also, the changes in the state of the environment are going to be observed by the agent. The combination of observations and the reward are going to tell the agent whether the action taken in that state was a good action or a bad action. So if it's a bad action, the agent learns or assigns a lower value to the chosen action for that specific state. If it's a good state, the agent assigns a higher value to the action taken in that state. And that's how it comes up with a policy of how to act in certain circumstances or in different circumstances. One class of reinforcement learning algorithms is Q-learning. So there's an action value function, Q, which as its arguments get the current state and an action that can be performed in that state, and returns the expected reward of applying that action in that state. And it tries to maximize this Q function. The Q-learning algorithm tries to maximize the Q function. Let us formalize the notion of policy here as well. So policy pi is a mapping of states to corresponding actions. It's essentially a function, or in a stochastic or probabilistic cases, it's a distribution that says what action should be taken at each state. So deep Q networks are one of the very first proposals in the hot field of deep reinforcement learning. They're deep. It means that they utilize the feature learning characteristic or advantages of deep learning. And they also solve a few other problems that previous neural network approaches to RL failed to capture. Like they solved the non-IID property of the gathered data by something called experience replay. They solved the problem of oscillation by fixing parameters, and they bounded the rewards by normalizing them to some limit. Normally that limit is between -1 to 1. So earlier this year, Arsalan and I, Professor Monir and I, published a paper on how to use adversarial examples to attack deep Q networks, or DQNs. In this paper, we first proposed a threat model for an adversary who may or may not have knowledge of the hyperparameters and other characteristics of the target network. So we considered both white box and black box attacks against DQN. We demonstrated that DQNs are vulnerable to adversarial examples at test time. We also demonstrated that DQNs are susceptible to transferability of adversarial examples. And we also proposed an attack framework for policy induction, for manipulation of the policy learned by DQN. So At test time attack, we tested two types of adversarial example crafting algorithms, FGSM and GSMA. You can see that in both cases, the attack was more than 80% successful for FGSM, and for JSMA it was 100% successful at all iterations or at different stages of training. Of course, this is a test time attack, so we stopped the training at certain times, did our test, implemented our test, and then let the training carry on afterwards. In terms of transferability, you can see that both methods are capable of generating more than adversarial examples that are transferable in more than 80% or 75% of the time, which means that black box attacks are possible and feasible against DQNs. As for policy induction, what we did was we came up with an analog of the black box attack methodology proposed by Paperno. So the attacker first trains a dual network, a dual DQN of its own based on his own policies. Then the attacker accordingly estimates the best action according to the adversarial policy, and this estimation is basically done using the trained DQN, the DQN trained by the adversary. The adversary then crafts perturbations to induce adversarial action, and the attacker applies perturbations to the environment or to the observations of the target. So our environment in this experiment was a Pong game. The target DQN was trying to learn how to play the game of Pong. And it turns out that this framework actually manages to manipulate the policy learned by the target quite successfully. As you can see, from the 20th epoch onward, the attacked policy completely diverges from the unperturbed policy, and it goes towards zero, which is the adversarial goal. The goal of the adversary, the policy of the adversary, was to make this DQN agent lose the game. And as you can see, this convergence is actually happening towards the 50th epoch. So what can be done to defend against adversarial examples? There have been quite a few methods proposed, like adding noise at test time, removing perturbations with a regular autoencoder, using generative pre-training, as in generate adversarial examples first and then train the network to correctly classify those adversarial examples, and so on. But it turns out that none of these methods are completely successful. In other words, all of these methods can be fooled. So there is, at this moment, no foolproof defense against adversarial example attacks on deep neural networks. And this is a very active topic of research these days. All right, very well. Thank you very much for listening to this presentation. If you have any questions, please shoot me a message on Slack or email me or catch me on Monday if you see me in the hallways. Thanks again.